Welcome back. In this MOOC we have focused on the photovoltaic materials that make a solar cell. However, for the assembly of solar cells into a PV module, more materials are being used. I will quickly introduce you to these materials in this video lecture. In addition, I will introduce a last important operation parameter of a PV module in the outdoors. We know that irradiance has an effect on the output of the PV module. In general, all other parameters being unchanged, higher the irradiance, the greater the output power will be. In this video, I would discuss with you the effect of a parameter of great importance, the module temperature. The learning objectives are to understand the impact of the PV module temperature on the performance of a PV module and to get familiarized with the materials besides the solar cells that are used in the assembly of a PV module. First, I'd like to answer the simple question: is a greater temperature better for the PV output or not? Or is PV output independent of temperature changes? In this graph, you see the IV curve of a PV module at a given irradiance and temperature. Now, if the temperature increases while the irradiance is constant, we see an IV curve that looks like this. So we see that while the current has very minimally increased, there is a significant drop in the voltage. This means that the overall power output has decreased. On the other hand, if the temperature were to decrease with respect to the original conditions, while the irradiance were constant, the PV output would show an increase. The minute increase in current with temperature can be explained with the fact that carrier concentration and mobility increase in the semiconductor with temperature. This is consistent with our basic understanding that a semiconductor, unlike a regular conductor, exhibits better conductivity with increasing temperature and is a perfect insulator at absolute zero temperature. The decreasing effect on voltage can be explained from this form of basic diode equation seen in the earlier weeks. While the temperature affects the various terms in this equation, the net effect of the temperature is that the decrease of the VOC is linearly. The magnitude of reduction varies inversely with the open circuit voltage. This means that cells with a higher open circuit voltage are less affected by the temperature than cells with a lower open circuit voltage. This means that a solar cell based on crystalline silicon with an open circuit voltage of around 0.65 volts will be more affected than, for instance, an amorphous silicon solar cell with an open circuit voltage of 0.85 volts. So now you have an idea of the effect of temperature on the PV output. But how do we quantify this effect? If the temperature of a PV module were to increase by, for instance, 10, 20 or 30 degrees Celsius, how would that output be affected? Well, the PV module manufacturers include what are known as the temperature coefficients in the data sheets of commercial modules. The temperature coefficient is nothing but the rate of change of a parameter with the temperature. For instance, the temperature coefficient of voltage is the rate of change of the voltage with temperature. The higher the temperature, the smaller the open circuit voltage will be. Similarly, temperature coefficients of power is the rate of change of the output power with temperature. A typical datasheet of commercial PV modules specifies the temperature coefficients for the power, the open circuit voltage and the short circuit current under standard test conditions. Given these coefficients, how do we calculate the PV output with respect to temperature change? We can use this simple equation. The term dx dt denotes the temperature coefficients of the particular parameter, being the open circuit voltage, the power or the short circuit current. Let's take a look at an example. If the maximum power output of a PV module under standard test conditions, that means a module temperature of 25 degrees Celsius, is 400 watt, and the temperature coefficient of power is 0.3% minus per degree Celsius, then the module's power output at a temperature of 50 degrees Celsius can be calculated as follows. A temperature coefficient for power of minus 0.3% per degree Celsius and a power at the maximum power point of 400 watt results in 0.3% per Celsius times 400 watt is 1.2 watts of reduction of power per degree Celsius temperature increase. The power at 50 degrees Celsius is then the 400 watts plus minus 2 watts per degree Celsius times the temperature difference 50 minus 25 degrees Celsius, which makes 370 watt at 50 degrees Celsius. As you can see, the sign of the temperature coefficient determines if the parameters is increasing or decreasing with temperature. In the exercises related to this video, you will be able to use this equation to estimate the effect of temperature on the various PV parameters. Note that there could be several factors impacting the heat flow in and out of PV modules. Encapsulation of solar cells is a major factor in increasing the operating temperature of the PV module. The eventual operating temperature of a module will be a result of the thermal equilibrium between heat generated by the PV module itself, the heat lost to the surrounding environment. The heat exchange with the environment in turn could depend on several factors like the ambient temperature, the wind, heat transfer coefficient between module and the environment, and the thermal conductivity of the module's body. Although the performance of the PV module is determined by the solar cell materials, to assemble a PV module, more materials are needed that have an impact on the PV module temperature. Let's look at the various materials and components. The junction box is located underneath a plastic or glass backsheet at the back of the PV module. The junction box serves at the interface between the conducting contacts of the panel and the DC input and output cables. This plastic box is designed for outside operation and to withstand heat cycles. Inside the junction box we can find a switch that enables all the cells to be either connected in series or some cells in series and some rows in parallel. This way the output voltage and the current of the module can be modified. Usually it also contains some bypass diodes. The junction box is connected to the backsheet material, whereas the solar cells itself are laminated between two layers of encapsulation foil to prevent air and moisture ingress. The encapsulation that provides adhesion between the solar cells and the top surface of the PV module at the front side should be stable at elevated temperatures and under high ultraviolet exposure. The encapsulant should also be optically transparent and have a low thermal resistance. The most commonly used polymer material is ethyl vinyl acetate, or EVA in short. EVA has a refractive index very close to that of glass, so the reflection losses caused by the encapsulation are minimal. EVA arrives in thin sheets that are used to sandwich the solar cells. The layers are then heated up to 150 degrees Celsius for polymerization and to create crosslinks that bond the module together. In this way, especially the metallic contacts can survive for many years. For thin film modules, the encapsulation is an important part of the module price. That is because these technologies use a transparent conductive oxide, or TCO, as a front contact. TCOs are generally very vulnerable to degradation by water vapor, which means that the encapsulant must be really good in order to enhance the lifespan of the module. Let's now focus on the backsheet of the module. Like the front, the encapsulation, the rear layer, must have low thermal resistance and prevent indiffusion of water vapor. In most modules, a thin polymer sheet, typically Tedlar, is used as backsheet at the rear surface. The front surface of the module is protected with a sheet of tempered glass. Tempered glass is a low iron content glass. It's low cost, strong, stable to make the module impact resistance. It prevents environmental factors like water and gases from damaging the solar cells as well. Tempered glass also provides excellent transmissivity in the spectral range the solar cells operate, as well as a low refraction in this spectral range, often realized with an additional anti-reflection coating on the glass surface. Highly transparent, impervious to water and gases, and has a good self-cleaning properties. That is the tempered glass. The final structural component of the module is the etching of or framing of the module. The sides are first sealed and then protected with an aluminum frame such that the module can be mounted on supporting structures. The aluminum frame should be free of projections which could result in lodgement of water, dust or other matter. Note that at the rear side an additional glass sheet may be used for added strength of the PV module. Let's recap. The performance of a PV module shows a dependence on the module temperature. Open circuit voltage and power outputs show a small reduction with increasing temperature, while the PV module's current shows an even more subtle increase with increasing module temperature. We have discussed how to calculate the external parameters of a PV module at a given module temperature in reference to the standard test conditions. Furthermore, we have discussed the different layers used to assemble a crystalline silicon module. The first layer is a front cover followed by two layers of encapsulant that sandwich the solar cells and the rear layer and a frame, ultimately providing mechanical stability to the PV module. In the last three videos, I have discussed some important aspects of PV modules. In a PV system, we would like to have a PV module operating at its maximum power point. So in the next video, we will discuss the component that controls this maximum power point, the maximum power point tracking. So see you in the next video.